Hi, good evening. Thank you all for staying all the way to the end of this really, really long day. I hope the last talk will be interesting and worth seeing. So my name is Drew, and I'm an infrastructure and data engineer at Strava. And this talk is going to be basically about how we've used Spark in a few applications to sort of unlock the potential of our data set. And so if you don't know about Strava, Strava is basically a social network for athletes. So we have about 30 million users, and on Strava you can upload your GPS data from exercise, so whether that's a run or a ride, or basically any sort of thing where you're moving outside, we'll take it. And we get around 15 million uploads every week, and overall we have like around 1.5 billion total activities. So the outline of the talk is, first I'm going to describe what that data set is more, and then I'm going to go into 3 different applications with a deep dive into the Global Heatmap, and then sort of summarize some thoughts on my usage of Spark at Strava. So what I call the data lake in its final representation now is basically our set of stream data. And what I mean by stream data is the raw array of measurements that's recorded from an activity. So streams can be of different types. So one type is elevation, another type is latitude and longitude. You can also have speed or time information, and then also measurements like heart rate or steps per minute or other things like that. So there are some examples there of what some stream data looks like if you plot it. So how we store this stream data for production usage is in a legacy format where each stream is a single file in S3. So we have about 10 billion files. And moreover, we use auto-increment IDs to key these files. So if you've ever used S3, you'll know that those are like really bad patterns. And it makes it basically impossible to do any sort of bulk analytics on this data set. So what I did about a year ago is I thought we really need some way of doing a cheaper bulk read of this data. So I put together sort of like my own data lake system where we are storing all the stream data in a compressed format in Parquet files, partitioned by just some partition key like timestamp. And so we can read 30,000 activity streams in a single file very quickly, and this sort of reduced the cost of a bulk read by like a factor of 1,000, and that's because S3 charges per read, and so doing 10 billion reads, they charge you a lot. And bulk read, it ends up being around just 10 terabytes of data reads, which with enough computers we can do really quickly and for almost no money at all. So now for the applications. Sort of the first one is a very simple one, and it's basically just a statistical model fit from running data. So this is to generate a model for a feature called grade adjusted pace. And so if you're not a runner, you might not know what that means, but it's basically a synthetic running pace that you use to correct hilly runs. So if you're running flat, you know how fast you're going, but if you suddenly have to go up and down a hill, it'll greatly influence your speed, and you might not be able to compare your performance with a flat run. So grade adjusted pace is basically a function to remove that error. So the common model that's used and that we used to use for grade adjusted pace was derived from a laboratory study of around 20 athletes running on a treadmill. And the new model was, I just fit it from actual running data where we have access to literally millions of runners and hundreds of millions of runs. So we can do a lot of filtering to find like really smooth data and a really well-sampled distribution of data at different gradients. And then also filter to draw data only when we know athletes are running at near their maximum effort, for example, in a race. So this is a comparison of the models, where orange is the new model. And this is just a measurement of the adjustment factor. So the lower it is, the easier running is at that gradient. And you can see that for uphill, there's a strong agreement because the old model measured energy. But the new model strongly disagrees with the old model for downhill. But it's much more reflective of how difficult running actually is. So for example, the old model predicted that at a 20% gradient, you could run twice as fast as you could on flat ground, and that's pretty easy to see that that's not true. Running downhill that steeply is actually harder, because if you try to run fast, you'll end up like stumbling, and it just requires a lot of energy output to not just crash. And then here's another comparison with stream data, and this is of a race on a really hilly race, and you can see that the old model had large drops in pace on the descents, whereas this runner was going all out for the entire run. And so the new model gives a much more uniform pace throughout their race, which is, tends to be more accurate. All right, so on to the next application, which is the Global Heatmap. And the Global Heatmap is just a direct rasterized view of all public GPS data points that we have in our data set. So that consists of 700 million activities. It's actually only data from the last 2 years. So that's over 1 trillion GPS points, 100 billion miles, or 100,000 years of cumulative exercise. And I think that, the input is about 10 terabytes, and the output is like half a terabyte. And that's basically just about 2-meter resolution of every point in the world. And there's also a couple different layers. So this is what it looks like. It's a public data set. You can look at it right now. You can filter to different activity types. You can see like runs or rides or activities on the water or activities on the snow. So how I built this, the whole entire thing is built in Spark. It's a very simple pipeline that I did almost from bare primitives. And it's actually pretty straightforward, so it didn't seem worth using any library that would bring in abstractions that I wouldn't have control over. So I'm going to basically walk you through all the steps. So the first stage is basically the rasterization. And so this is like a cool picture of why rasterization is neat, where you can see sort of the streams converging as boats go under through a bridge with pillars. So you can't go where the pillars are, so you can see that the heat sort of changes. So how rasterization actually works is there's this tile math coordinate system where a tile is basically a 256 by 256 unit of pixels, and the whole Earth is tiled. And then there's also a zoom level. So at each higher zoom level, you have twice as many tiles, and a pixel has twice the resolution. So the actual heat map renders everything at level 16 zoom. So that's like, 2 to the 16 tiles by 2 to the 16 tiles, and then each of those is 2 to the 8 pixels by 2 to the 8 pixels. But of course it's sparse, so if there's no data, there won't be a tile there. So you can kind of see the math of how to generate the actual tile and pixel for a single GPS point. And so to actually rasterize the data, we're basically taking an array of, it's like basically vector data, because the GPS points come with double precision. And then we're going to discretize this by just sort of drawing which pixels the paths cross over. So the simplest and fastest algorithm for this, it has to be really fast because it needs to be run, trillions of times. So there's the Bresnahan line algorithm, which is just a way of making a straightforward way of drawing pixels between a point that's extremely fast to implement. And so there's going to be like 7 trillion of these pixels that get drawn in, and they're aggregates too. So for each pixel, we're just aggregating the total counts of activity streams that cross over it. And also there's about 30 million of the tiles that are not empty. So that total is about 30 terabytes if you don't compress it, which when you're actually adding these things, you can't compress it because they have to be in memory. So a nice trick there is you just make a ton more tasks than there are cores, such that your data goes from being compressed GPS vector data to like a few working tiles at once, and then is immediately recompressed as soon as the tasks finish. So that you never have to allocate 30 terabytes, unless you're like Apple or something where that's no problem for your Spark cluster. So there's a fun boundary case that comes up in rasterizing, which is that to map points on tiles, you basically are doing a group by on sections of a stream that are in a single tile. But what happens if a stream goes from one tile to another? So here there's a blue tile and a red tile, and they might be on completely different machines because you're doing a group by tile, and you can't there's no way to make continuous all neighbor tiles on like the same machine. You'd always have edge conditions to take care of. So a simple trick for that is as a pre-processing step, you basically just add in a virtual point at every boundary on the tile, such that all of your subsequences of points will always end on the edge of a tile. And then you just don't have to worry about this problem anymore and can pretend that it doesn't exist. And there's a bunch of other tricks that I don't have time to go into to make the data look good when you rasterize it. So one thing is that a lot of GPS devices will correct the GPS data onto the nearest road. Because if your GPS data is wandering all around, that might not look good if you're visualizing a single activity. But if you're aggregating and visualizing millions of activities, then that correction looks really bad. So you can see in the top, you get these nasty little one-line pixel areas. And so we just add some noise to every single activity that is in the same distribution. You just see a normal GPS noise, and that then causes smooth data, like you can see in the bottom. All right, so after rasterization, you basically have these raw counts of every pixel. So the data there can range from 1, which is the minimum amount, to like probably tens, if not hundreds of millions in really popular areas. So to actually visualize this data, we have to normalize it into a bounded range. So this image here shows my favorite example of well-executed normalization. And this is in San Francisco, and you can see the bright area as a bike path where there's millions of rides, and then there's a faint sort of path and fuzzy distribution inside of the top right area, and those are actually swimmers. And so there's probably about like 4 orders of magnitude less data there. But we're visualizing it all on the same screen, and you can clearly see there's sort of separate distributions. So how I did that is a really clever general and parameter-free solution. So there's no parameterization needed. And I basically just used the cumulative distribution function of the raw pixel values, such that each pixel gets mapped to the percentage or percentile of where that pixel falls in all of the pixels in the tile it belongs. So to actually implement this, you do some sampling so that you don't have a huge complicated CDF. So you can sample just a few of these values, and then to evaluate the CDF, you can just do binary search in that small array. So I think I just do like 256 samples, and then that's really fast to binary search when you actually evaluate this. So as I've described that solution, there's still a problem, which is that this normalization function is computed on a per tile basis. So you take your samples in a single tile, and you have your CDF there, but then if you go to the neighboring tile, again, it's going to be computed on a totally different Spark worker and have no knowledge of like if there's a way popular route nearby. And so there'll be a discontinuity along the border of your normalization function. So you can see, I hope everyone can see, there's a really obvious example in the top right, and then if you like look carefully, there's some other examples of artifacts between tiles. And in general, if you have something like this, it just becomes really obvious of like how the tiles work, especially as you see them load, and you can see the adjacent tiles, there is a mismatch. So how we can solve this is the first thing we do is instead of taking a CDF of just a single tile, we can take a CDF of the tile and the pixels in adjacent tiles. And if you do that in like a circular radius, you'll get like a much nicer blend of normalization functions that you go from one tile to the other that isn't sort of part of this square tile pattern. So that's one part. Just with that, that wouldn't be enough because you would still have a change of CDF across tiles. It would just be a lot less. So the second component of that solution is basically bilinear smoothing. And when I first thought of this, I actually forgot what bilinear smoothing was and tried to solve this problem, and like I reproduced it and is like, oh, that's bilinear smoothing. And then I thought it would be way too expensive to actually do this, because to do bilinear smoothing, every single pixel has a unique combination of weights with 4 other CDFs from the 4 nearest tiles. So basically, every single pixel of all like a trillion pixels is like has a separate normalization function, but together that will make a really nice blend so that the weighting will be completely continuous. And it's really satisfying to sort of get this finally right and have like a completely artifact-free normalization. But of course, so both of these steps also require another Spark stage of grouping a tile with its neighbors and then reducing to get some combination, either the sum of CDFs or just using the 4 neighboring CDFs to then normalize every pixel in that tile. So here's another before and after of that original image, and you can see that the one on the right is now completely smooth and there's no tile artifacts. And then this is a larger comparison of an old version of the heat map that didn't have this normalization with a new version. And you can see that without a smooth normalization, there's this harsh transition where you get away from the dense activity in the city into these ferry tracks through the San Francisco Bay. And on the right-hand side, you can see that once you get away from land, the ferry tracks smoothly become visible again. So this gives like a very nice sort of high dynamic range effect when you really zoom out. And you can also see that in the upper left, a lot of the roads are visible on the right that weren't on the left because they were too close to this main corridor of cycling, and like they just completely zeroed out the heat for any other road nearby. All right, so far with rasterization and normalization, I've only talked about doing things at the zoom 16 level. And while those steps are expensive, it would be really expensive to have to process from raw stream data the same data set again and again at every other zoom level, which goes from 16 all the way back to 0. So there's some shortcuts in order to generate the same data and get to render all the tiles for every other zoom level. So this animation is basically showing every single zoom level. It's not a tile, it's actually centered over one point, but it's a nice representation of sort of what this process would look like if you could visualize it. Yeah. So the core step here is yet another group by and reduce function, where 4 tiles, neighboring tiles, are reduced to 1 tile in the next zoom level after you've zoomed out. So to implement this, you would just have a group by and then a reduce, where your reduce is basically downscaling your pixel data so that each pixel is going to be the sum of 4 pixels divided by 4. And you do this in one stage for the whole world at once, and then you're left with a fourth of the data. I'll actually jump ahead to this. And so this is sort of a nice visualization of how much data is written after every layer. And you can see that it's sort of exponentially decreasing. And if you've ever had a Spark job that does something like this, it's probably like the most satisfying thing in the world, because you know that once your first job is finished, it's like a guarantee that all the other ones are going to, because you're not going to run out of memory or anything like that. And the runtime like also gets exponentially faster up to a point where like, the first stage will take an hour, and then like the last 5 levels will take, like 2 seconds each. And it's just awesome, especially because the actual final layer is like all of those trillions of points in like a single tile. So the actual like pseudocode for this, I actually did implement it recursively using Spark APIs, which is nice. It was the first time I got to do that. So you can, you start with data in Zoom, you normalize the data, and then you write that data to your sink, and then you recurse with data passing to a zoom out call, which will reduce the size, and then passing in one less zoom level. All right, so then the final step I hinted at with the write function is how to store and serve this data. And so after all this work of like getting away from the inefficient S3 storage, I was sort of faced with this problem of not really having a way to store all of these tiles. And I didn't want to write 30 million S3 files. Well, actually way more than that, because there's 5 layers and 16 zoom levels. So I sort of at a loss of what to do. Then I had this idea of that I could basically just group adjacent tiles and store them in one tile. But then that didn't, so like if you do that just crudely, so you do, like an 8 by 8 region of tiles, you're going to get some areas where it's just like a very small amount of heat of just a few people. And then that whole block will still be like very small once it actually gets compressed, because we're of course storing this tile data compressed. And like the variation in how much space any particular tile region takes up is huge. So you basically want to have like a dynamic approach so that you're storing different sizes of file blocks depending on how much data there actually is once it's compressed. So there's another recursive algorithm to do this, and there's probably a name for it, and it's probably not the best possible approach, but it's what I came up with and I use. So basically what you do is you start from all tiles and you sort of view it as a quad tree, and then you aggregate all the tiles, aggregate the size, the file size, the compressed file size of all the tiles at every node, and you basically just walk up this tree in parallel until you exceed a threshold. And then once you've exceeded that threshold, you write all the tiles that are descendants of that node into a single file. And then you can store the manifests of all of these paths in your tree. So like as a cute visualization of this with just a little bit of data, here's an example where let's say that there's tile 1, 0, and 2, 2 are like cities or something, so there's a lot of data there. And so those are sort of going to be stored at zoom level 2. So we'll remove them from this process. And then we go to the next level where we find 2 more tiles, the purple tile, which is now 4 subtiles, and then the green tile, which has 1 tile that we already stored, so there's only 3 left. And then finally, after this, there's everything else, which is that weird 7-tile region shape on the top. So I haven't actually looked at like I haven't actually plotted this, and it looks like you could get some really weird shapes. But in practice, it tends to work really well because most of the people are looking at areas where there's a lot of heat, and so therefore the files there will be stored at the lowest levels and will be nice and continuous. But maybe there's a whole nother approach to this problem that is better. So the actual persisted data is going to be 1 byte per pixel. And that's because we want to be able to visualize the heat map in different color maps. So there's sort of no point in applying a color map transformation, which would require you to have RGB channels when you're going to want multiple ones anyway. And then you just have more data to store. And it's actually extremely cheap to do the conversion to a colored PNG at read time when you're serving this file. And the vast majority of tiles are never actually going to be served. They just have to sit there and be ready in case someone wants to read them. And once they are read, then they get cached by CloudFront also. And that's just because if like some part of the heat map is linked somewhere and a ton of people are viewing it, we don't want to like do all that work again and again. So we'll just let CloudFront handle that caching. So that's sort of the end of the global heat map deep dive. And so the final application is something that I'm still working on. It's sort of like is the latest project that we're doing in Strava Labs, which is called Cluster. And so the idea behind Cluster is we take the same data set and we do spatial clustering of all the activities in order to find sort of clusters of activities. And in this sense, a cluster of activities under spatial clustering is basically just a route that a lot of people use. And there might be variants on that route, but there's sort of one shared feature that all of those activities participate in. So in this example, which is the heat map of activities in a single cluster, it's the main running loop of Central Park. And you can see by plotting the activities in it as a heat map sort of where people go to this running location. And it's a very different visualization than showing all activities, because all of these activities have a common destination. And then once you have that data set, we can aggregate other facts about the cluster, such as sort of what time and date people go on that activity. So here's some examples of different clusters. So one of them is just a regular running route that people do every day on the top left. And in the top right, there's a commute route. You can see that no one rides that on the weekend, and they only ride it during commute hours, both AM and PM. So it's actually not directionally sensitive, so it will include the reverse routes as well. And then there's, in the bottom left, there's a running race, or a common running area that's actually near the city here. And so people there are running that route either before work or during lunch break, which is a very sharp peak, or after work, which is a much smoother peak. And you can see that there's a few people who do it on the weekend, but most of it is on the weekdays. And then finally, there's a running track, and people only run there in the evening on a few days because that running track is not otherwise open to runners. It's used for other sports as well. And then on the far right, you can see how a map view of this data set of clusters, which are now sets of activities, can be extremely useful for sort of exploring what routes there are worldwide. So this is just a list of the most popular marathons in the world, ordered by how many people sort of matched into that category. And you'll see this is my token attempt at AI to fit into this conference. And you can see some very bad NLP. So if anyone has advice on how to have better NLP, I'm interested in suggestions. And so how this actually clustering works, this is too complicated and should be its own talk. But basically I use locality-sensitive hashing. There's a brilliant new algorithm called super min hash, which is asymptotically faster than min hash. And that basically goes on quantized shingles of points. So we again map the raw vector GPS points onto discrete tiles, and then we do a min hash over the sequence of tiles for each activity. And then once we have that sort of min hash signature for every activity, we can do this extremely fast comparison of how similar two activities are. And if you do that inside of a similarity join, which is basically you're taking sets of all activities that collide on one of these min hash signatures, you can then find a really efficient way to harvest a bunch of pairs of highly similar activities globally. And then once you have that, you can sort of think of it as a graph, and you can run some fast graph clustering algorithms on that. I've just been using single linkage clustering because it's really cheap to execute. And then, but it tends to have false positives, so then we'll split apart the clusters again and sort of recluster. And there's probably some other ways to do it, but it's really hard to do this in parallel because you're dealing with hundreds of millions of activities, and the number of edges is also quite large. I don't know exactly what it is, but probably trillions. Yeah, so now for some final thoughts just on Spark. So we have a pretty small Spark shop, and we're running vanilla Spark on Mesos on AWS. We have everything containerized and complete isolation of Docker images. We have a very simple auto-scaling script that just scales up if there's unscheduled tasks on some Spark framework on Mesos and prevents scaling down of anything that has a Spark executor, because that's really bad if your job isn't finished. And then for the heat map itself, I've been running it on a cluster of around 100 instances, and it takes something like 5 hours. Keep in mind that's like for 5 different layers, so you have to do almost the same thing 5 times, where each time you're filtering to different types of activities. And finally, just some lessons. So one thing is that there's sort of endless parameter tuning, and I think that parameter tuning is sort of unavoidable if you care about performance or cost, and you're using a distributed system. Because if you want to use a distributed system, you sort of like have to have something that doesn't fit into a single machine, and then you might as well fully utilize all of the machines that you're now spending money on. We also use Scala, and I think dependency management is sort of the worst part of that, especially in Spark, and when you have a ton of other libraries that have dependency conflicts. I've also learned a lot about optimizing, and with Spark jobs, you can't really optimize locally. You really have to profile on a real cluster and the particular instance configuration that you want to run in production. This might be like an obvious lesson, but it's sort of hard to learn until you've really been misled by some local optimizations that are actually like taking the completely wrong trade-offs. Because you know maybe your prod cluster is bound by I/O, but your local cluster is bound by CPU, and then you just do the totally wrong direction of optimization. And I think it was worth building everything from scratch here because it really is something that's sensitive to performance and cost for us. And it wasn't really that hard, and now there's no abstractions that get in the way of making other changes to the system if I want to do some other version of it. And I can also think about how it all works as a Spark program too, which is really nice. It's a lot better than using some really complicated Spark algorithm that like does 50 stages and you have no idea what they are until you dig into the code. And then you still won't really know how you can change any of it because it's part of a huge framework. And there's probably still a lot more optimizations. It's kind of foolish that I don't use a GPU. But I think that would probably only make one stage really fast, and there'd still be a lot of other stages that would be quite slow and would also need optimization. So it's not like a order of magnitude speed up or something. Yeah, so resources, the heatmap URL, Strava Labs, which has some other projects. Most of them work. Our engineering blog, we're hiring a lot of people. And then the cluster itself, it's actually offline now, but it'll be back online eventually. Yeah, so that's all.
Thank you, Drew. Questions? Questions for Drew?
Yeah, so for normalization, it looks like you have a lot of local sort of CDFs. Would there be an advantage to having a global CDF, or do you actually need the sort of local CDF so that it looks normal across the whole globe?
I think you need it to be local, because otherwise you could imagine like one city might just have like 1/10 of the users as another, and it would look different. So this is nice, because the nice part about the CDF is locally there's always the same distribution of pixel values, so it sort of always looks the same, which is really cool.
Hey, do you continue to feed back users' activity data back into the heat map to like change the model over time?
Yeah, so right now the update cadence is a monthly release, and it's like data rolling over the last 2 years. So there's new activities, and then old activities are gone. Activities that are deleted are deleted.
I'm a Strava user, and I really like your app. I'd just like to know about the data set, what's available and what's like proprietary. If I wanted to like, I noticed on your website you have some scope for like people building apps on it. Can you just talk a little bit about that?
Sure. So like as a Strava user, obviously your own data is yours. And then we also have an OAuth API system, so you can build an app on Strava's platform, and then you can get consent from other Strava users to use their data. And exactly what you can do is complicated, and you can look at our API or developer docs for that. But basically, if other people opt in to use your app, then you can have some access to their data in an informed way, similar to most other OAuth applications.
But what about stuff like
routes? What?
Like public routes, like you know, like people like the standard routes, so that are sort of publicly available. You know, like after I've basically like gone on a ride or something. You'd have all these segments. That segment data, I think, is public, right?
That's right. Yeah,
okay.
There's public pages for all the segments, and if your routes are public, they're also publicly available. But you can make them private too.
Okay.
Yeah.
And one last question, just a little quick. You guys, you have like split data for runs. but not rides, and cyclists really hate that. And there's been people like, who have gone to your website and bitched about it for the past, I think, 4 years.
Yeah.
And I'm really still not sure why you guys don't allow us, cyclists to like have split. That's a really pet peeve of mine. I have to literally go to map my ride to get that.
Yeah. No, that's a good point. There's definitely a lot of pet peeves, and I think it's almost impossible to be feature complete with all the things that people want.
But you have it for runs, so from a programming perspective, it's already there.
Yeah,
all you have to do is turn on, pull a switch, right?
I'm not going to defend that decision. It takes a lot of time to plan and design all this stuff. Yeah.
All right. Okay. Thanks.
Awesome.
Yeah, exactly. Yeah, come work for us and fix it.
Awesome. All right. I think that's all the questions for now. Thank you, guys. Thank you for coming.
Cool.